Okay, we're going to do a couple examples. First example, locomotive exerts a constant forwardly directed force of 400 kilonewtons on a train that it pulls for 500 meters along a straight run. How much work does the engine do on the train during that period? Uh, well, for part A, quite simply, the force is equal to 400 kilonewtons, or 400,000 newtons. So that's our force. Our distance or displacement equals 500 meters. So work equals force times displacement, and we know this is a straight line problem. I mean, it's in a straight run, so there's no angle. Force times distance, quite simply 400,000, or 4 times 10 to the fifth times, that's a 5, times 500 meters. When you do that calculation, you get 2,000 times 10 to the fifth, and units are, that's a newton times a meter. A newton times a meter, that's a joule. So if we, write this correctly, it would look like this. Work equals 2 times 10 to the 8th joules. That's the answer for part A. Part B, we're coming towards the station, and the locomotive slows the train. Okay, applying a constant force of 100 kilonewtons in the opposite direction. How much work does it do on the train over a distance of 1,000 meters? Okay, so for part B, what do we got? Part B, our force is equal to 100 kilonewtons, and it's in the opposite direction. So we've got a negative 100,000 newtons, and I'm only converting it to newtons to put it into units that we're somewhat used to, a little more used to, I should say. Uh, how far are we displacing this object, or how far is this object displacing under this constant force? 1,000 meters. 1,000 meters. And so work equals force times the distance or displacement. It's not in an angle. It's all acting in parallel along the horizontal. So our work is actually negative work. Negative 1 times 10 to the 2, 3, 4, 5, 6, 7, 8 to the 8th joules. Our next problem is a work at an angle problem. We've got a truck here that's dragging a stalled car up a 20-degree incline. They tell you the tensile force in the tow line, and that's acting at 30 degrees with the road. Here's the road. Okay, the road is the yellow line. That's the road. Okay. Uh, so it turns out in this problem we don't really care about the 20 degrees, because we're displacing up the hill. I'm going to use a different color. we're displacing uphill. Okay, our displacement is uphill. And we want to know what force is causing that displacement uphill. What is that force that's causing that displacement uphill? And we want to know how much work was done. Well, it turns out we do know the force that's causing this displacement, but it's not 1600 newtons. Why? Because 1600 newtons is acting at 30 degrees. Okay, it's acting at this 30-degree angle. So we want to know specifically what the force is in the x direction in order to get the work. So how do we do that? Just looking at our formula for work at an angle, work is equal to the force, the magnitude of the force times the cosine of the angle times the displacement or the distance. Plugging in our numbers makes this pretty easy. So when we plug our numbers in, we get 1600 newtons times the cosine of 30. Why are we using 30 degrees? Because we want the angle measured from our surface that we're displacing on times 500 meters. We take the 0.5 kilometers and we change that to meters to put it into fundamental units, and we calculate. When we calculate, we get 6.93 times 10 to the 5th joules. That's how much work the tow line or the truck acts on the car as it pulls it up the incline. The next problem is one where we're overcoming the force of gravity. We've got a 1 kilogram block that's raised at a constant speed through a vertical distance. Vertical just means up and down, of 2 meters. So we know our height is equal to 2.0 meters. Okay, determine the work done on the block by the hand, okay, in overcoming gravity. So the hand is applying a force upward, okay, on the block and is raising it. So for determining that work equals mg times h. The mass of the block is 1 kilogram. That is already in fundamental units, so we don't have to convert. G is 9.81, and the height is 2.0 meters. Multiplying all of this, we get work equal to 19.6 joules. So work done in overcoming gravity. Our last problem says that we've got a youngster who weighs 250 newtons, so that's the youngster's weight. He's sitting on the grass holding a dog by a leash, and the dog pulls on the leash with a force of 100 newtons. So the leash is dragging this kid the dog is dragging the kid via the leash at a constant speed, and he takes him 20 meters straight across the yard. Okay, we want to know how much work did the dog do on the child and overcoming kinetic friction. Well, immediately people will go and say, well, my work and overcoming friction formula is work equals mu force normal times the distance displacement, and that's mu k, and completely forgetting where this actually comes from. And where this comes from is the fact that this is force of friction. So, before you jump to that, you got to think to yourself, they're not giving me the coefficient of kinetic friction. Why not? And the reason they're not is because the dog is pulling on the leash with a force of 100 newtons. And he's dragging the kid at a constant speed. And so you have a situation where the force of friction is equivalent to the force that the leash is pulling. Okay, so this is equal to the force applied, or the force tension in the leash, and it's also the force of friction. Okay, it's also the force of friction, which simplifies this entire problem pretty easily, and simplifies it to where that's 100 times 200 meters. I'm sorry, 20 meters gives you work equal to 2,000 joules, or 2 kilojoules, or 2,000 newtons times a meter. Okay, understand where joules comes from. Okay, it's newton, a unit of force, times a unit of distance, meter. One thing to keep in mind is the weight of the youngster didn't come into play here, but if they had given you a situation where if they said, hey, the kinetic coefficient of friction is, I don't know, 0.4, and they didn't give you the force the dog pulls on the leash, well, then we could figure this out if we had mu k. We know the weight of the kid. We know he's sitting on the ground, so force normal equals force weight. So in this alternate situational universe, we could solve it with this equation, because work would equal the coefficient of kinetic friction times force normal times displacement, and we plug in our numbers. 0.4 for mu, force normal is equal to the weight because we're sitting on a flat surface, and we're still pulling him 20 meters, let's assume. So work in this situation is equal to, a pretty lucky pick by me using 0.4, that would be another 2,000 joules. I guess it would have been nicer if I had picked a different coefficient. And if I had picked a different coefficient, you can see that it would have a different work. Just happened that I happened to pick the perfect coefficient to correspond with the problem. Woohoo.